Sure. So, hello. Today I'm going to talk about firmware assisted kernel dumps, like taking kernel dumps with the assistance of firmware and how it can enhance the reliability of the kernel dump process. I am Aditya Gupta. I'm part of Linux Technology Center at IBM. Okay, so going forward to the agenda of what we'll be seeing today. First, I will be covering an overview of the current KDump infrastructure, which is the default way we get kernel dumps on almost all distros or most architectures. So we will go through the overview of KDump, and then we will go through the concerns of KDump. Like, what are the inherent issues that come by design of KDump that we want to fix with FADump? So we will be going through the inherent issues, and then we will talk about FADump, which is firmware assisted dump, as an alternative to KDump. I will show how it works and all, and we will be talking about it from a generic perspective as a technology which other architectures or other uh, platforms can also implement. We'll be seeing the components needed for FADM. This also gives you an idea what things are needed on your platforms. And we'll go through the real life examples of these two platforms, P series and Power NV. In in a power system, in a IBM Power hardware, it can boot in two modes, either the virtualized mode or the non-virtualized bare metal mode. The virtualized mode, when it's booting, it's called a P series, and when in the non-virtualized mode as a bare metal, it is called a Power NV. Both have a different firmware, and both are treated as a different platform, so we will get a good idea from there. And then I will end with the flexibility of KDUM, where we can get the good things also of KDUM utilized with FADUM as well. Okay, going to the overview slide. So KDUM, uh, short for kernel DUM, is basically the current technology, current infrastructure in the kernel to capture a VM core out of a crashed kernel. The idea behind a VM core is similar to how you have a code dump in a user space application. So let's say you have a user space application, it crashes. The system can give you a code dump file. That code dump image is something which is the memory snapshot of the crashed program that you can debug and find out later why the program had crashed. Similarly, in case of Linux, we have something called a VM core. This is the equivalent of a code dump in a user space application. So VM core is a system's memory snapshot. Basically, it contains everything that was there in the kernel's memory, which crashed, which you can then later copy it to somewhere and debug it with tools like GDB, Crash, or Dragon. There are various tools to debug, but we will be talking how it's created, like before that. So okay, with the idea of kernel dump set, like with the VM core set, KDump is a technology where it uses kexec to capture the dump. So how it happens is, let's say your first production kernel is booting. While it's booting, it reserves some special memory area, which is called a crash kernel area. In this case, you see the blue part of the memory, which is the full system RAM. And then inside it, there is a that pink memory region that is the crash kernel, that is the reservation where a second kernel is loaded for the event of a crash. Like that will come in the event of a crash. So our first kernel is booting. We reserve some memory and load another kernel, which is generally called a crash kernel or sometimes called a kterm kernel, capture kernel. For simplicity, I might be calling it a second kernel in this case. So in during boot, it's loaded. The second kernel is available. So what happens is at time of crash, in the event of a kernel crash, the kdump infrastructure knows that it has to kexit to the next kernel, to the second kernel. Since the first kernel is crashed, it cannot take a dump of its own memory itself. It needs to give the control to the second kernel to do it. So the second kernel is started in that pink region. It will only touch the memory region in that reserved section, that pink area, and the blue portion of the memory will be untouched by the second kernel. So the second kernel boots, it gets the information that what were the kernel pages getting used by the previous kernel. And then with that information, along with these untouched memory, which were part of the previous kernel, that blue area, it exports a file called in the path /proc/vm core. This is the VM core that you will be copying and debugging it later on. So to summarize, the idea is first kernel boots, reserves some memory, loads a crash kernel, loads up, we call it a panic kernel also. So loads a crash kernel in that reserved area. And in the event of a crash, the kernel knows that it has to k-exec to this. Okay, so
The crash information will be kept in the pink area or different
which area? Which information?
trash information like a status of memory.
Yeah, so status of memory and everything will be in the proc VM core. So that memory will also contain your page table, whatever structures you have for like what are the memory regions and all. So that complete information is there in the blue region. So it all is in the blue region. The pink region is just the memory that the second kernel also needs some memory to boot, right? It needs to touch some memory. So that memory is just for the second kernel. Everything related to first kernel is in the blue region. Going forward with the concerns with the inherent issues with the design itself that occur with kdump base, as you saw that we are depending on a crashed kernel to k-exec to the second kernel, which is supposed to take a VM core dump. So this inherently doesn't feel very reliable. Like you are trusting on a panicked kernel, crashed kernel, which any subsystem can be wrong. Any subsystem could have issues. And we are trusting on it to boot us into a new kernel. There can occur any issues between this transition. So that is one major issue with the design.
This
And the
new,
second,
new kernel that we jump to, where does it reside? Like, is it already loaded at boot
it's
time?
already loaded. So
So it's somewhere in the RAM itself.
yes, in that pink area. So I said that like while the first production kernel is booting, it reserves this region and it loads a crash kernel into this. So that is generally done with the kexec-p. Yes.
What is crash kernel? Like, it's the same Linux
It's
kernel
just
running.
another kernel, Linux kernel. Generally, generally it will boot with limited resources and limited drivers, but it's just a Linux kernel.
So is it packaged as part of the same Linux image that you usually boot, or is it like some special packaging that you do at the time?
It can be the ditto same image that was the production kernel image. You can use the same kernel.
Oh, can it be a non-Linux kernel?
Kdump doesn't work that way. Kdump expects a Linux kernel. Maybe by design, if you can make something else, but Kdump for Kdump purposes, it will be a Linux
So when it
kernel.
goes to the crash kernel, does it pass some different parameters to let that kernel know that it's now a crash kernel kind of?
Yes, yes. So there's a thing called a elf core header, which will be passed by the first kernel to the second kernel in the parameter. So what happens is second kernel needs a way to know that what were the memory regions getting used, or what was the CPUs, how many number of CPUs were active and all. So those needs to be in a header called a elf core header that the first kernel saves while crashing.
Why not a crashed kernel will monitor the first kernel? If that crash, then
So-
automatically they can be taken care of.
So it's like only one kernel is executing at a time. There are no two kernels parallelly running to monitor. So only one kernel is running. First time the first production kernel is running. After it crashes, it jumps to the second kernel. So till it jumps, there is like second kernel is not running, so it cannot monitor.
So there is some pause.
There
some,
is
delay.
there is
implementation or
there is no pause. Only delay you can consider it from the moment of crash till we do a kexec jump. That might be considered as a delay, but otherwise there's no other delay.
So usually when the kernels panic, right, it go to some reset vector.
Yes.
Is that managed here?
Okay. So
Does it make things such a way that instead of going to the reset vector, it comes to the exact kernel?
so that reset vector generally in our let's say in PowerPC case itself, we will end up in the die path or the panic path. That will come in the normal panic or die path only. Even the reset kernel will be registered by the kernel, right? When the kernel is booting. So even those are taken care. So it's not a different path. Even if you go to the reset vector, those are the kernel's reset vector only. So it will come again.
That kernel is already there in memory. So
Right.
once first kernel die, give second kernel can start the execution.
Yes.
That one. So because all the boot stack or oops message already is there, and then it gives some time to load that. Kernel already is there in memory. Just start the first execution. Then whatever minimum task is there, just copy the VM code dump. It will dump the dedicated partition or path that has been already given to that secondary kernel actually part at the. So might be there some will be some flag or register. So if that crash happen in that register itself,
What?
see,
Register.
like there must be some communication. See, from kernel first to kernel two. First kernel when it crashes there, second kernel is already in that booted is there in memory. So okay, so now first kernel is almost die. Okay, if anything is there in register, it will be override by that first kernel will boot and it is not taking register dump, it is taking VM core dump and block memory, whatever idea is there, it just try to copy that one part, that boot part. And it will take minimum register and that set to load and copy part.
Yeah, so I'll try to simplify it. It's just that, see, the communication that is happening from first kernel to second kernel is via that core header and some arguments that kernel arguments it can pass. So as I said, the second kernel is being booted via kexec. Kexec allows you to pass any command line, right? So there you pass, like these are the elf core header. Elf core header will have the CPU nodes, memory details, everything. And then you can pass any other argument also. So second kernel knows that it is a crash kernel. Both are
Second kernel gets loaded only at the time of the crash.
no, at boot time, because at time of crash we cannot rely on loading.
What is your storage driver size? But
Yes,
if you
you
have
can
like
say.
but if you have like a region like a CMA,
Hmm.
so that crash kernel memory.
So crash kernel is in this case it's reserved by memblock itself. We are not reserving via CMA. So it's reserved. No one else can use this. So this is not a CMA reservation.
I mean, later there is a CMA region that is added to KDUM, right?
There was, but the catch there is. So okay, for context, I'll go to the concerns with KDUM slide. Uh, you mentioned about CMA, right? If you notice the second last point here, so for everyone, the context he's saying is the memory is reserved, right? No one else can use it. So there was a feature that was introduced for CMA reservation, where that reserved region can be reserved as a CMA region and it can be used by the user space. So that is not wasted. In a way, it is wasted. On a real system, we are on a big system, we are reserving anywhere around 2 to 4 GB, and that is not available during the whole production kernel boot to the production kernel. So there is a solution to that to reserve it as a CMA region. Like CMA is something which can be used if you mark the region as CMA, that can be used by the user space processes. One catch is if you are using CMA, you will not get user space pages in the VM core. Like it might be incomplete, which is generally okay with us. In a VM core, we want kernel pages. So regarding CMA, KDUM does support CMA, but even the upstream kernel documentation says don't use it unless you are okay with the incomplete or incorrect dump. Other
Yes, but I think I now remember. So even with CMA, the minimum memory for the kernel is still reserved as like your memblock only.
yes,
But the memory that the kernel will use, like your crash kernel will use for its own operations like KMLOC or like any other memory, that can come out of a CMA area. So instead of let's say you're reserving the 4G completely for the entire crash kernel, you still have to reserve something for your crash kernel minimum memory so that you can keep your crash kernel. But the rest of the memory allocations that needs to be done for the crash kernel can come from CMA.
that can come from CMA, but for now we reserve the whole 4 GB. Even if we are loading a smaller kernel image, we reserve the whole
Yeah,
4
without
GB.
CMA.
Yes,
When
without
you
CMA.
don't use this CMA. Correct.
Yes,
correct.
we don't use CMA because there is a chance that. So okay, let me come back to this
Yeah.
again. It will make sense. So first issue was depending on the crashed kernel to load another kernel. That itself feels very unreliable. Then the second major issue which caused the idea of FA dump initially is that the devices are in an inconsistent state. Imagine your kernel is running, devices are doing something, devices might be doing DMA, uh, your disk drivers are running, your network drivers are running, everything is running. Suddenly you switch to the next kernel. The next kernel gets all the devices in an inconsistent state. The devices were doing something, and now the second kernel is getting those devices. So in this case, when we are depending on the crashed kernel to jump, our devices were never reset. So there is one way which the kernel suggests to reset those devices is in the second kernel, you pass that kernel parameter to reset devices. But even that has issues because to reset the devices or device drivers in the second kernel, you need support of something called soft reset. Like imagine soft reset is something like where you are resetting the device, but you are not doing a power off, power on cycle. You're just resetting the device state. That may not be always there. Like for new devices, it won't be there. So many times it occurs that you will see Red Hat or Oracle advisories on their websites that some so and so driver is crashing in the kdump kernel during initialization. So that those kind of situations are likely to happen due to the inconsistent state, and if the soft reset has not been done or not done correctly, thus initialization, since you are again initializing the same drivers in the second kernel, those can fail. So that is one unreliable aspect. And one more, that CMA issue also comes up due to these devices being an inconsistent state only, because CMA is, if you let's say reserve the kernel region, second kernel region out of a CMA region, the in CMA user space can be executing, user space can be using the CMA region. So possibly there might be a DMA happening, like direct memory access might be happening. So when the switch happens from first kernel to second kernel, there is no one to stop this DMA. So it is possible that the user space that started DMA to the CMA region, the DMA might still be going on while my second kernel is booting, which can corrupt the second kernel's memory. So basic idea here is everything, the root cause is the devices being in an inconsistent state. That causes the TMA issues, us not being able to use CMA. Everything is due to the devices in an inconsistent state. The last very minor concern compared to the other one is there is a brief service lapse in case of hot add or hot remove operation. So on a running system, if you are adding more memory or removing a memory, adding more CPU, removing CPU, you remember I told that the first kernel transfers something called a elf core header to the second kernel, which has this memory. So on every hot add or hot remove, the configuration of the system is changing. The memory regions changed, the number of CPU changed. That needs to be updated. So every time a hot add or remove happens, the elf core header needs to be changed. And if a crash is happens in between this brief amount of time where the elf core header is being updated, we will get an incomplete dump. All these are hard to recreate, hard to debug issues, which can occur due to the inherent issues of KDUM.
Why don't you quiet the devices, right? Only the
So-
target device is what your
Yes.
kernel is worried.
Yes, so
You
that
can
has to
always-
come
you
from
can
the
always quiet the, it's becoming a justification, right? You can always quiet the rest of the devices which you don't really care. As long as you have the proper reset handler for the target device, at least or something, or the network device, you are good.
yeah. So that's the catch, right? The driver needs to support it. If drivers are good, it's okay. But thing is, in a running kernel, there might be so many drivers, so many devices. All of them needs to be good.
So
Any
you
of them.
can quiet it in the KDM kernel, right?
No, Quaz as in that Quaz is just pausing the device operations,
Yeah.
right? That has to come from the drivers. That logic has to come from the drivers, right? So that again brings us the same soft reset issues where driver might not support it.
So the elf core header, is it in the crash kernel region or the blue region?
In the blue region, we give a address of the elf core header to the next kernel.
So that is also prone to corruption.
No, because elf core header is reserved in the blue region, and blue region will not be touched at all. Will only be read by the second kernel. So that is preserved.
I have a good question. So following up on what Vasant was saying, right? So how do you do a safe shutdown? You would end up reusing driver infrastructure to do coicing anyway.
Yes. Yes.
That becomes unreliable for you to use during a KXX or
No, thing is, in a normal boot, that is okay. Like we are anyway shutting down, but in this case, we are crashing. I want the image to debug why it is crashing. So uh, for production cases, this is very much required. I want to debug why some crash happened. So if that was happening in a shutdown case, okay. Anyways, I was shutting down. It's gone. It's not a safe shutdown. Agree. But if it happens in a KDUM kernel boot, then we lose the chance to get the VM core. Second kernel won't boot. So we lose the chance to get the VM core itself, which we needed to debug. So basically, that is the difference. Like, even if normal shutdown, if it would happen, if it would have happened, that is something like that again will go through the KDUM path. But anyways, in KDUM, the thing is we don't want to lose that VM core. We want to have it debug later on. Okay, this time is available. I will go to the next slide. So to as an alternative to the KDUM, we IBM came up with something called firmware assisted dump as an alternative to the KDUM design. So instead, previously, like how there were two major issues, that which was depending on the crashed kernel to boot the second kernel, and that the devices might be in inconsistent state. What firmware assisted dump does it changes the design. So now what happens is if you see that blue memory on the right side, right? Uh, let's say production kernel is running, and while booting, it again does that similar crash kernel kind of reservation. It does a reservation, and then when it and registers with the firmware that okay, if I am to crash, if I crash, you handle the flow. Like there, the firmware needs to support such a hypervisor call or edge call, some feature with which the kernel can tell the firmware while it's booting in the first kernel boot that okay, in the event of a crash, please handle the flow.
The firmware is kind of running at a different execution level on the same
Yes.
core.
Sometimes it can be the same or different, depends on the architecture. But in bare metal, it might be the same. But
Because I'm wondering if it's like I come from an ARM background, so if it's like sitting in an external like an MCU core in the same chip, maybe that's not possible. Right? Or is the solution scaling there as well?
I don't have much idea about the ARM or NCU there, but that depends on the architecture, like how you want to implement it. We'll go through examples of it, how that is done. But for now, we can just assume that okay, there while the first kernel is booting, we register with the firmware that if a crash is to happen, please handle the flow. And when a crash happens, the kernel does a call similar to reboot, but with a special flag saying it's an abnormal reboot, or maybe a different edge call itself for an abnormal reboot, abnormal termination. In that case, the control comes to the firmware. Firmware preserves the memory region, copies the memory regions. Firmware takes care of getting you the CPU registers, and firmware takes care of resetting all the devices. So the second kernel which will be booted by the firmware will be after a proper clean reboot. Like the firmware is taking care of resetting everything, and and it will basically do all the reset things that it used to do, just other than resetting memory. It will not reset memory. That is a special thing. Other than a clean reboot, only special thing with firmware assisted dump is it will preserve the memory. It should not reset the memory. So this way, the second kernel, when it's booted, it's just like another production kernel. In this case, second kernel is not booted by kexec. It's booted by the usual flow, which our first kernel would also gone through. Just that the firmware will add some device tree property or some way to tell that this is after a crash. So that the second kernel knows it has to take a dump. But for all other aspects, the second kernel is booted through the same flow that first kernel also went through with the devices reset in a clean state. So this time we are depending on the firmware to boot us, which is at least more reliable than a crashed kernel. And we are having all devices reset, so we don't get any DMA ongoing issues or the device reset issues. Okay, so this is
How does firmware reset the device to?
firmware goes through the all initial IPL initial steps again. Like it's let's say for PCI devices, it will go through that bus level reset. Like all the devices themselves connected to the PSBs, like post brace, those will just get powered off in a way.
It's like
And
power
then-
off only, right? Like, so in driver, you were like, you hope that the driver does the reset by literally resetting the memory.
Yes,
Here, you are just saying that it's sort of like I pluck the power out for a while because firmware can
for
control
many
that.
things. Yes. Like PCI devices, it can be that way. You're basically doing
It's
that.
like a warm reset effectively, right? Or does it
You
literally
can-
go to?
you can say-
because some devices have this absolute
It's not a
resistor.
cold reset for all devices. Some like uh, like yes, agreed. Many it will be a warm reset. Yeah, done by the firmware. I will show in a real flow, then we'll get a better idea maybe.
In this case, you don't need a crash kernel, right? Because
We-
the regular kernel would boot up
Yes,
and
we can.
copy this reserved memory to the target.
Yes, the crash kernel is just the terminology for second kernel. We can again say that it is a crash kernel.
But in this
But
case,
yeah.
you have crash kernel memory also reserved.
We have that reserved memory you see there, right? But that is not for
That
the
is
crash
memory
kernel.
Where you
Yes.
copy your proc VM core or production kernel memory, right?
Yeah, so that is, yes, crash kernel is not loaded there. So that is one
So
difference.
where is the crash kernel?
There is no crash kernel here because second time when the firmware starts another boot, that is the crash kernel itself. Like that when
Actually,
it's
production
booting.
kernel is starting.
Yes,
Again,
production
and
kernel is
then
starting
from
again.
reserve memory, it capture the data,
Yes,
copy to the KDM target,
yes,
right?
yes.
So you don't need crash kernel, that pink region which you have shown in your earlier.
Yeah, we don't need that pink region. So
In a
One-
hypothetical, is that possible that we can have active kernel, a standby kernel? If active kernel crashed, a standby kernel take care of all those services and all.
So that is something which is not there currently. There was some patches for multi-kernel support or something like that upstream, where a multiple kernel can run side by side and that kind of thing. Maybe that technology can in future do that. Currently, there is no such thing in the kernel. So this firmware,
Sorry, I'm a little bit confused by this diagram. How much memory are you consuming compared to your previous diagram, right? I
Okay.
see capture kernel, production kernel, backup kernel, like what are
Okay.
all these? What is this
So-
again, capture kernel here?
so I will.
Because as you told, we are not reserving that pink region. So why the capture kernel?
The thing is, if you see here, the pink region is where the second kernel was booted. It will
No, no,
it's
but
booted
in
at some random.
in a FADM scenario,
Mhm.
you don't need this pink region.
True, we don't need, but still we need some reserved memory.
Ah, yeah,
To-
that is okay. That is for your firmware to copy,
Yes,
right?
yes.
That is the reserve.
But what do you copy there?
But for kernel also, let's say second kernel will boot, it will, if we just let it run, it will override the memory, right? We want the first kernel's memory untouched. So that blue region that is there, that is for the copying that boot memory region, which will be used by the second kernel. If you see that blue box on the right side, that is the second kernel booting. So it is using that area, that blue area. So that will be getting overwritten, right? By the second kernel.
Basically, what you're saying is here you are loading the capture kernel.
Yes,
This memory is getting copied here. So
Yes.
that the original kernel is not kind of overridden by the capture kernel.
yes. Yeah, that's the idea.
Yeah.
Okay. So one note with this is currently supported only on power, but the idea is in rig and possibly be implemented in other architectures. I will go to the components needed. This is a more detailed flow in a way harder to talk about, but yes, the here, let's say we are in a FADM boot. What happens? In the first kernel, we start at the top left box there, which in which firmware has reset everything. This includes memory also, and it boots the kernel. Now, the green box that you see there is something we need the your platform or other architecture to implement. So there should be two APIs for FADM to work. First was it was registering with the firmware, right? Like if a crash happens, take care of the flow. So first is in that green box. First is we need an API to register for firmware assisted dump. So this API generally it has things like how much memory regions, uh, what memory regions to preserve by the firmware. Uh, it also needs to allocate some memory for the firmware to put the CPU data in. Like firmware needs some memory, right, to where it should put the CPU data, CPU registers and all. So those memories and any other hardware data which you might want from the firmware. This depends on your architecture. There can be things like metadata, what is the boot memory size, etc., etc. And first was the API to register for FADM. Second is we need a API to inform the kernel that a crash has happened, like some abnormal termination has happened. Like I will briefly go to the next slide. Like here, if you see, we have two platforms on IBM Power, which is one is virtualized P series, other is Power NV non-virtualized. In this case, both have different firmwares. On left side, you see that for these two, register and abnormal termination, we have these two H calls. These are called RTAS calls, but for the sake of generic being generic, we'll call it H call. So for registering, we have an H call, let's say called configure kernel dump, which will basically get the memory regions the firmware is supposed to back up the memory region for firmware to put CPU data in, and other API is that abnormal termination, other H college for that OS termination that you see that there OS term. This is for the virtualized Power P series platform. Here we see both are new H calls that were introduced to support FADM. But in Power NV H calls, which is the bare metal, non-virtualized, you see again there are two different things for register and abnormal termination. There is a call called register tag, and there is one MPIPL update uh, H call also. There are multiple H calls for registering different data. We saw other hardware data, remember in the previous slide, that you might decide if you want to take that in a single H call or have multiple H calls for all of them. So in this case, Power NV is one example where you have multiple H calls in that register. So register is not just one H call here, it's a series of separate H calls that you do for different types of data. So, and abnormal termination, what we are doing in Power NV is, let's say if you don't want to introduce a new H call itself. So that is what Power NV does. It reuses the tech reboot H call, which was already there, but it gives a special flag to the H call that it's a M- MPIPL reboot. MPIPL here is memory preserving IPL, memory preserving initial program load. So MPIPL is basically same as FADM, just called as MPIPL in Power NV. So the idea here is, as you can see, P series chose to implement both of them as a separate H calls, and Power NV, on the other hand, reused the reboot H call with a flag for abnormal termination and introduced multiple H calls for the register sequence. So similar to this, you can choose how you want those APIs to work in your firmware. But the idea is at least one for register and one way to tell abnormal termination. The bottom code snippets show the interesting parts that we give the firmware. Those the memory regions that we are giving in both of them. So they are common. The idea is common in both of them. So let me come to this. So after you have registered with the firmware, if a kernel crash happens, then the second API you inform the firmware that a crash has happened. Now it's just a simple H call that you make in the kernel. So no kexec is involved here. You just do a H call. The kernel gets to know, the firmware gets to know that abnormal termination has happened. The control goes to that pink box, that firmware. The main things that the firmware is expected to do is use the CPUs, just pause operations, get me registers, preserve the memory regions, that like how we preserved in that blue box. Those memory regions can be preserved. Give me CPU register data and any other data you might want. Let's say hash page table entries if you want. If you want any metadata, whatever is supported by your firmware, you can request all that to be put in some memory region. Then firmware, the last thing firmware does is it is expected to add a hint, some way for the second kernel to know that it's a boot after crash. For that, in PowerPC, we modify the device tree to provide a flag that okay, this is after crash, and then we do a memory preserving boot. This is basically the same idea of resetting devices, but not the memory. Skip resetting memory and do the reset. Now the second kernel boot, as you can see, either it can use the memory that is there in the memory regions it had expected, or if your firmware supports extra things like the metadata and all, it you might have to provide a API to retrieve the structures from the firmware for the second kernel to get data from the firmware. And then now it has everything resolved. Now the flow is same as kdump after this. Like uh, you have all the memory regions, you have data on what were the memory regions, what are the CPU registers, you export a slash proc slash VM core, and after this it's the same story for FDM and KDM, so that I will not be covering till the generation of VM core. We are going through it. This is the overall flow. I will give some real examples for both of them. Let's say in case of we have these two platforms, right? T series and Power NV. In case of Power NV, the flow will be like this. So the Linux, the first production kernel is booting. The L part there is like a VM. Like it's a logical partition. The Linux is booting in it. During boot, it registers with FADUM and like what memory regions it wants to be preserved by the firmware. It registered with that configure kernel dump hcall, which was the hcall for P series. And then firmware will internally store whatever configuration. Configuration here is basically what memory regions to preserve, where to preserve. That the firmware stores and the Linux keeps running. At the event of a crash, the Linux kernel, instead of doing a simple reboot or something, it does a hcall to signify that to the firmware that an abnormal termination has happened. So it does the OS term hcall to say that okay, abnormal termination has happened. Firmware, when it gets the call, it checks if FADUMP was ever registered. Like in a normal case, when you are not even registering for FADUMP, we don't want the firmware to do extra things. So if firmware assisted dump was registered, then the FADUMP flow starts. The flow is that same that we saw in the previous diagram. Pause the CPUs, get the CPU registers, copy the memory regions to destination memory regions. This destination is basically the blue box again that we saw in the FADUMP.
Last 1 minute.
We'll
Did you handle the,
complete it.
did you solve the early boot crashes
Early boot crashes as in?
before the registration happens?
No, we cannot do anything. So
You haven't solved it.
that is there we don't have anything. Like if the kernel crashes
You
in
haven't
there,
solved it.
no, it's not solved. No. But that is the same with KDump also. Like unless you load
I know.
load the other kernel.
I know.
Yes. So yeah, that is not solved. If something happens that early, then we can do nothing about it. Currently,
You have not solved it, right?
no. Yes. So like here, after the FADump has preserved, given the registers and all, it reboots. It does a clean reboot, where the second kernel will boot, and it will basically again have all the memory preserved of the production kernel, and have registers and all to proceed. We'll quickly show the more complex case of Power NV, where the firmware is not a simple just one firmware. The firmware also has relocation and all, and it's like a multiple sequence of things. The Opal you see there is the firmware. SB is the CPU boot engine, and host boot is another one early stage of firmware, you can say. So as you can see here, there are more things involved, but the idea is same as this P series one. The idea is as simple as register and abnormal termination. This way, in Power NV, it goes through this flow where it registers. Again, it has multiple register calls if you see for different things. So there is a special feature called metadata that OPA supports. So that also is used. Then abnormal termination. And then Opal, what it does is it goes back to the start to, like, you can say it's like a square one. It triggers the SB S0 reset. This reset, what it does is it restarts the I step flow. For people familiar with the initial program load I step flow, there are the hardware boots like this, like I step 1, 2, 3, 4, 5. The different I steps have different responsibilities. So it goes through that path. So everything is reset. Only thing is the memory reset is kept. The I steps which would have done the memory reset is kept. So in this case, you can also see that SB after collecting the register also stops the core and cache clocks. So the clocks also are stopped. So everything is reset. And then it goes through the normal boot where Opal is booted, Linux is booted, and so on. So this is the flow. That there are different terminology like that MDST and MDDT. Those are source and destination table. Those are internal details of how this is handled. This is the flow. I will. This is my last slide. I'll just end with things like there are some benefits that KDump had, like in the second kernel. If its only job is to capture a VM core, it doesn't need a lot of things. So you can basically optimize the user space, optimize the init or capture kernel. So this is generally done in KDump. KDump uses a special init for the capture kernel. In FADump, we are going through the again normal boot, so we are using the same production init which we might not need. So for that, we have special ways like we have scripts in the init itself to decide if it's a capture kernel. We don't initialize a lot of drivers, just do the basic things like disable use pages and all. And so that is done. And one more, like, so first two are basically to have a smaller boot for the second kernel. Here, if you want, you can not have a second capture kernel kind of boot. What FADump design allows you itself is you can boot a production kernel again, capture the VM core, release all the production kernel memory, and continue as a production kernel. That also is possible. So if you don't want a minimal kind of second kernel, you can basically boot a second kernel, cap production kernel again. That way you basically save a second reboot. That is one feature which we are not utilizing, but by design that feature is supported. Then the third point, zero cost memory reservation. As you saw in KDump, we were reserving 2 to 4 GB memory, which was basically not available for the production kernel in the whole full time while it is running. Here, FADump, since the kernel is not needed to be loaded beforehand, we can use that reserved memory. That blue area that you saw is reserved and marked as CMA. So user space can use that memory. So there is no wastage that is occurring there due to that reservation. So that is usable by the user space. One catch with this is since we are using CMA by default, you don't get user space memory in the VM core. If you want user space memory, which is generally rare, generally we just want the kernel pages to debug the kernel. If you want user space memory, FADump also supports a no CMA option, which will make it behave similarly to how crash kernel reservation was there in FADump. So, and all these with the reliability of having a clean reboot with the devices in a sane state. I end my presentation. This is the typical legal statement. Then my presentation, I have added support for FADump in Chemo and some firmware bits. You can see these to see what can be implemented at the firmware side. For the kernel part of FADump, there is this file PowerPC kernel FADump 3. It's in the PowerPC architecture files, but it's very generic enough. Like people like Mahesh, Hari, and Saurabh, they have made it very generic, where you can register more platforms to it. So even now, this part is generic. The platform code is in separate files. Maybe in future we can make it a generic platform. Then this file will basically come out of the pod. That's it. Thank you.
Good session. Any questions? I know we overrun. Take few questions, then you can discuss.
Or I can take questions offline.
So fine. Okay. So we have light refreshments in the main hall, so we can go and have it and we'll meet again. Thank you.
Thank you.
Nice presentation.
Very
easy, understandable.
Was it understood? Yeah. Like, was your point clear? Like, did I answer
Not
it?
quite.
Okay.
So what I was asking is, shut down the kernel. You would anyway need to quiet device because you can't shut down the. Yes. So his question was,